everyone. Thanks for being there at this conference. First, we would like to thank ROMHACK for accepting our talk remotely because, restriction related COVID-19 make really difficult travel and other things. So we are really sorry for that. The title of our talk is Making Your Own Stuxnet, Exploiting New Vulnerabilities and Voodooing PLCs. So behind this title, we would like to show you how we were able to build a new Triton, a new Stuxnet type attack by relying on our own vulnerability we have previously found. So first, who are we? I'm Nicolas Delhaye, and I've been a vulnerability researcher since 2010. I currently work at Airbus Cybersecurity, and in my job, I enjoy looking for vulnerabilities targeting both the Windows OS and whatever application running on it. So he's also my workmate Flavien Dola. He has been a vulnerability researcher since 2009. He's specialized in embedded systems such as IoT, ICS, onboard components, and so on. I would give you a shout out to Guillaume Orlando because he helped us a lot to develop some exploit and to integrate all these vulnerability into a great demonstration. And thanks to him, we are able to see some demonstrations, some videos about our vulnerabilities. So just a few words about the agenda. First, I will give you the context and I will give you an overview of the attack scenario we have considered. In such scenario, we are going to chant 5 vulnerabilities, allowing us to compromise a PLC from an IT access by targeting the engineering session. We will see later on all these vulnerabilities. And before wrapping up, we will give you some key takeaways. If the time allows it, we will have a Q&A session at the end. So companies which own an ICS are many companies dealing with energy, water, and so on. And for a long time, security risk wasn't taken into account into such infrastructure because these systems are not intended to be connected together with other networks. But now people like working remotely, systems can be administrated remotely, and so systems are more and more connected together. And unfortunately, this kind of systems relies on many software, many hardware components, leading to a large attack surface. And there are at least 2 well-known APTs that works in that way by targeting the engineering station to compromise a PLC on the OT network from an IT network. The first one is Stuxnet and second one is Triton. Both of these malware are targeting 2 different manufacturers. For the first one, it was Siemens, and the second one, it was Schneider Triconex. And in our case, we are inspired by these APTs to build our own APT, but targeting other components. In our case, it was a Modicon 340 PLC. This is a PLC really used in the industrial world. And we are targeting as well the Schneider EcoStruxure software running on engineering stations. So like I said, we want to compromise the OT network by targeting the engineering station because this engineering station can be both connected to the IT network and the OT network at the same time. Even though recommendation advocates not to connect such a station both on the 2 networks, in the real life you can see that, but you can also imagine that this station is first connected to the IT network to do some stuff, and then disconnected from this network to be connected to the OT network to do what this station is intended to do. The engineering station is intended to do for example, loading a new programs, update a new programs on PLC, and at this moment, if the engineering station has been compromised, the OT network is in danger. So what we need to achieve this kind of attacks first, we want to find a remote control execution to access the engineering station from an IT access. then it will be great to get full right on this station. So looking for local privilege escalation seems quite good. And then we want to find a way to interact with PLCs without user interactions. And finally, we want to execute unconstrained code on the PLC. That is a code that is not limited by the use of APIs, because when you use the graph-set language, you can access some APIs such as the sockets functions, and we want to be able to call this kind of function. So we will see at the end how we were able to realize that. So now I leave the floor to Flavien about how to access the engineering station.
So, hi everybody. So in the ICS world, when you want to make an automation program, you have to use a specific software depending on the PLC you want to program. So in our case, the PLC is a Modicum 340, and the name of the software which allows you to program it is Control Expert. And Control Expert and most of the engineering software provide a very cool features called the simulated PLC. And with the simulated PLC, you can test your automation program before deploying it on the real one. So here is the workflow. You design your automation program with the language you choose. So for example, ladder or GraphSet, and then you compile it and then you deploy it in the PLC. And as the physical PLC, the simulated one is listening on the 502 TCP port. And the protocol behind this port are Modbus and UMass. And the good news from an attacker point of view is that the 502 TCP port is open on all the network interfaces without any restriction. So we can try to inject our own program on the simulated PLC using this port and try to get a remote code execution on the engineering station. And maybe we have some security mechanisms to bypass, like sandboxing mechanisms, stuff like that. So let's see how an automation program is deployed. So in order to look at the format of our compiled automation program, we must do a little of reverse engineering in a Control Expert. So we identified functions in codeengine.dll that are in charge of the compilation step. And you can see at the right top of this slide that the classes ending by engine are in charge of the compilation step. So by making a little research on our favorite disassembler, which is IDA, we can see that Control Expert is able to build an automation program for 3 different architectures, which are ARM, Sonix, and Intel 32. In our case, the simulated PLC is running on a classical computer, so the CPU architecture is Intel 32. And in order to identify which function were called, we put some breakpoints on all the methods of the Intel 32 classes. And at the end, we saw that our automation program was transformed to Intel 32 native machine code. So this is very interesting because maybe this native code is executed as it by the simulated PLC. So I mean, without any check or any sandbox mechanisms. And yes, that's the case. In fact, if we patch the native code generating during the compilation step with our own shell code, and that we let Control Experts deploy it to the simulated PLC, then our shell code is executed. And you can see at the right of this slide that our malicious calculator was started by the simulated PLC process. So there is no sandboxing mechanisms. So great, now we've got our remote code execution on the engineering station. Unfortunately, we faced 2 other problems. In fact, the first problem is that the PLC simulator accepts just 1 connection at a time. And in real life, the simulated PLC is starting on demand when the user wants to test the automation program. So there is a high probability that the legitimate user is connected when we will try to exploit the simulated PLC. So we must find a way to disconnect the legitimate connection. And this connection is managed by the UMass protocol. And UMass is a very, very old protocol designed by Schneider Electric. And as it's very, very old, this protocol lacks of cyber security mechanisms. For example, there is no ciphering, authentication features, and also there is no correlation between the TCP session and the UMAS station. So this protocol is vulnerable to a man-on-the-side attack. And also, UMAS is not a very, very complicated protocol. So just by doing a little of reverse engineering on the simulated PLC stack, we identified that the UMAS session ID is only stored on 1 byte. So it's very easy to brute force it. So you just have to send 256 relays reservation frames to disconnect the legitimate session. So now we can connect to the simulated PLC and try to send our exploit. Unfortunately, there is another problem. By default, Control Expert advises users to start the simulated PLC with a protected project inside. So if you do not know the password of the project inside the simulated PLC, you are not allowed to load a new one. And this protection was originally designed to protect intellectual properties of the automation project. So if you don't know the password, normally you cannot access to the data inside it. For example, you cannot access to the ladder code inside the project file. So Schneider Electric decided to use this protection to also protect the simulated PLC access. And we'll see that it's not a very good idea because one of the first experimentation we made was just to do a network capture during the authentication. And we saw something very strange. In fact, there was no network traffic when we validate the password. This means that all the information needed to make the authentication was transferred before by the simulated PLC to the client, and the authentication is done on the client side, not by the simulated PLC services. So it's very bad because the client side can be controlled by a malicious person. So you just have to send back the right function code, meaning, okay, authentication succeed, and you can gain access to the simulated PLC. So now we are able to connect to the simulated PLC and send our exploit, and we've got our remote code execution on the engineering station. Okay, and just to go a bit more deeper, we doing some additional reverse engineering tasks to locate the function in charge of checking the password of a protected project. And we found another mistake in its design. In fact, if we patch this function to always return true, Control Expert successfully opens the project despite of the password you provide. That means that there is no correlation, ciphering mechanisms or stuff like that between the password you provide and the data inside the project. So in a nutshell, this implementation makes the authentication mechanisms very inefficient. So now we will show you a little demo of the remote code execution on Control Expert. So for that demo, we adapted the industrial simulation system named GRFICS. And this system is a realistic simulation of a chemical process reaction. So as Nicolas said before, we want to give a special thanks to our workmate, Guillaume Orlando, who did an amazing job in the exploit development and their integration into this ICS platform. So as you can see, at the bottom, we have the computer which is in charge of simulate the chemical process. At its right, we have the PLC Modicon 340, which is driving the automation of the chemical process. At the top left, we have the supervision screen. And at its right, we have the engineering station with Control Expert inside. So we considered for this demonstration that an attacker already infiltrates the network. So he have a direct or indirect access to the same network of the engineering station. Okay. So in this demo, the attacker will exploit the three vulnerability that I described before. First, he will disconnect the legitimate UMAS session. Then he will bypass the project authentication. And then he will load his malicious projects in the simulated PLC. And finally, he'll get a remote code execution on the engineering station. And after that, he will duplicate his access to his command and control server, which is on the internet. And then he will not need any local network access anymore to continue his attack scenario. So let's see this beautiful demonstration. Oh, Okay. Okay, so at the top left, we have the attacker console. At the top right, we have the command and control console. At the bottom left, we have the engineering station with controller experts inside and the simulated PLC started. So first, the attacker scans the network on the 502 TCP port to see if there are any Modbus server. So after that, the attacker sends a specific UMAS frame, which gives him a lot of useful information, like if it's a simulated PLC, the version of control expert, the path of the project loaded inside. And of course, all this information is getting without any authentication, just by sending one UMAS frame. So thanks Schneider for that. So now we start to exploit the simulated PLC. So first, we disconnect the legitimate UMAS session. That's why we have the message PLC communication fails that appear in Control Expert. Then we bypass the authentication, and then we upload our malicious project. And when the simulated PLC executes our project, we've got a reverse shell. Okay, so now the attacker can forward his reverse connect shell to his command and control server. Okay, so now the attacker no need local network access anymore to continue his attack scenario. So great. Let me back to the presentation. Ooh, it's not, okay. Okay. So I found the same vulnerability in another ICS manufacturer, which is ABB. And in the ABB case, the simulated PLC is listened on the 102 TCP ports on all the network interfaces. And control builder std.exe is in charge of transform the automation program to x86 native code. So as the previous attack, just by patching the generated machine code, we can execute our own code in the remote target. So we've got a remote code execution in the ABB simulated PLC. In a nutshell, we can conclude that this vulnerability class, which is getting a remote code execution on the engineering station just by injecting native code in the simulated PLC. So this vulnerability class is certainly present in many other ICS manufacturers. It's a good news from an attacker point of view, I think. Okay. So now I let the floor to Nicolas. So he will explain to you how he can elevate his privilege on the engineering station.
Okay, thanks to my workmate Flavian, we have an access now on this engineering station, and it will be great to get full right on this relevant target. So we are looking for local privilege escalation. So if you have to deal with neither environment, we will probably come across with EcoStruxures Control Expert software, also known as Unity Pro. And what is pretty interesting from an attacker point of view with the large attack surface that will be offered to us. And after looking at what component seems relevant to me, I chose the Modbus driver component. I chose it for two reasons. The first one is it's a service running with system rights. Of course, it's better to get full rights on the station. And then the service is deal with shared memory, which is accessible for any users on the system with all rights on this shared memory. So when you encounter such a planetary alignment, you are very likely to find a vulnerability. But however, it's not straightforward to exploit because you have to properly abuse the shared memory by locating all the relevant offset you need to patch in order to reach the vulnerability. You also have to find a way to control data to override the file you want to target, to send data into it. And there is also some restrictions writing, for example, to the length of the file name, you can overwrite on the file system. We will see later there are many other restrictions. And another one is to find a relevant executable to overwrite the file with the data you want to use. So here's the basic architectures of Modbus communication in order to understand what the components involved to this local privilege escalations. So on the left side, you can see a user interface that's the Modbus client running with a standard user right. And this interface allows us to configure the serial channel here to exchange with the PLC on the right. All the data you set in this interface will be written into the shared memory. And for example, you can see the COM1 string here at the bottom with the COM1 string on the left side. And then the services will read this shared memory to really configure the serial channel. Now imagine if a malicious program opened the shared memory before the services read the COM1 string. The COM1 is like a file finally, and the malicious program modifies the COM1 string by any file on the system. Then the services opens this file with system rights. So now the next step will be to find a way to write data into this file. And what I noticed was to use the TCP channel here at the middle to send data to the PLC throughout the serial channel. So at this moment, you got an arbitrary file write leading to a local privilege escalation. However, like I said a few slides ago, there are some limitations. The first one is related to the length of the file you can write, you can overwrite. And in our case, we are limited to 13 bytes. And it's not enough to overwrite a file, for example, under the system32 Windows directory. But to bypass that, you can think about NTFS junctions and object manager symbolic links. And there is a great article written by Clavoyot named An Introduction to Privileged File Operation Abuse on Windows. And I really advise you to read this article if you want to know more about that. Another restriction is related to the amount of data you can use to overwrite the targeted file. In our case, we are limited to 1042 bytes. And of course, it's not enough to build a new standard PE. So thinking about tiny PE is a better idea I got. So after Googling, I chose the PTS Tiny P GitHub project. You can, through this project, build a hello world PE of 402 bytes running from Windows XP to Windows 10. So it's exactly what we need for our exploitations. And the last one, not the least, is to find a targeted executable running, of course, with system rights. The first idea that can pop in your head is to overwrite a Windows file. But in fact, with system rights, it's not sufficient to overwrite this kind of Windows file because you need the trusted installer right. So the best idea or the best thing to do is to look at a binary which is embedded with the software you are targeted. In our case, it was Schneider EcoStruxure software. So after looking at what the components is the more relevant to exploit the vulnerability, I chose the NAMBP.x binary. So before watching the demonstration about the local privilege escalation, just a few words about the context so as to not getting lost during the video. So the malware is executed from the remote control execution that Flavien had just presented to you on the PLC simulator, and now the malware requires system rights to get full control of this on the engineering sessions. So the first step is the attacker of the malware request to the CNC for elevating its privilege. then the CNC informs the malware about files to download to exploit the vulnerability. For example, the create symlink binary, the LP binary, which is in fact the exploit itself, and the download and exec binary, which is the tiny PE. Then the CNC informs the malware about commands to execute with this binary. For example, what is the parameters to use, and some other commands such as the logof command or the command related to clean all the mess during the exploitation. And finally, the download and exec binary results in downloading a new malware, establishing a new session with system rights, of course, this time. So now we are going to see the demonstration. So on the top, you can see the shell on the CNC. On the bottom left, you can see the engineering session with the EcoStructure software in foreground. And now we are listing the session. This session has been created during the remote control execution. So we want to interact with this session. And now the init command allows us to know if the driver, the Modbus driver, is running on the system, and if we have an administrator privilege. In our case, we don't have this privilege, so we are playing the exploit. So while the exploit is occurring, we can see on the bottom that the CNC is downloading the binaries I just presented a moment ago, and is executing some command. For example, you can see now the creation of a symlink to bypass the limitation about the length of the file name. You can override, and then the attacker, in our case for this demonstration, has to enter the press, the touch enter to initiate the cleanup of all the mess happening during the exploitation. And why there is a logof command? Just because to call the binary we are overwritten, we need to send a logof command. And when the logof command is sent, we got two sessions because the binary is called twice. So now through the init command, we can see now we have administrator privilege. So that's all for this video. Okay, so now we have full right on this station, and we'd like to interact with PLC without user interaction, and we are looking for intrinsic or hidden function that has okay. So what we want is to inject new payloads on the PLCs by using the most reliable approach, and of course without user interaction. So why not rely on how a developer, a project already works? That is by starting a new project, launching analyze and build commands, and sending useful commands like start, stop, or download command. But we want to realize that without user interaction. So as an attacker, you need to study how the software works. After some research, I like to thank DCOM Technologies with these reusable components that help us a lot to achieve this kind of attack. So here is a case study based on DCOM to show you how we were able to interact with the PLC from a malicious executable without user interactions. It's not straightforward because you can't access the control expert component right away, and this component as all we need to interact with the PLC, you have to interact with the broker component. So the first thing you have to do is to instantiate the broker component. So how can we realize that? So first you have to retrieve the class ID to instantiate this component. So after looking at the Windows registry, you can use the right class ID with the create instance method. And as soon as you call the create method with this class ID, you can see the PS broker binary created on the engineering session. And now if you look at some members composing this object, you can see the new application method or the open application method. And both of them require a string, that is the name of the application you want to create or open, but also returns an iApplication interface. So now we'd like to know what we can do with this iApplication interface. So after opening an application, you can see first some binary executed on the engineering station, like the control expert binaries or the trace server binaries. Fortunately, all these processes are executed in background, so there is no interface popping into the screen, so an administrator or a developer can see there is something wrong happening in the engineering station. So now if we look at some function composing this interface, you can see one quite interesting, which is the set PLC connection address that allows to set the IP address of a specific PLC. So if you look in more details at what this AP requires, you can see an iProject interface. So how can we retrieve this iProject interface in order to call this method? And if you look at the last member, you can see the project property, and this one returns exactly the iProject interface. So now we'd like to know what we can do with this iProject interface. So after calling the project property with the true flag and listing the members composing this iProject interface, you can see exactly what we need at the beginning of this part of this presentation. For example, the analyze and build command that allow us to compile a new program, but also you can see a very interesting function, which is a transfer all PC to PLC method that allow us to download, to push the binary you have just compiled and build to the PLC. The PLC, you have previously set the IP address through the set connection IP address, something like that. So at this moment, you have all you need to automate the infection of PLC without user interaction from our malware. So what else? Now I leave the floor to Flavian about how to design and execute PLC and consent code.
Okay, so now we are in the engineering station and we will try to corrupt the physical PLC, and we will use the same way than the APT Stuxnet or Triton done before. I mean, we use the engineering station to corrupt the automation program inside the PLC. So in our case, the PLC is a Modicon 340, and as the simulated PLC attack, we saw that the automation program is translated to ARM native code. And also, there is no sandboxing mechanisms in the PLC. So in a nutshell, by hooking the compilation process, we can inject our own ARM bytecode, and we will let the control expert deploy it for us. And finally, our code will be executed in the Modicon 340. But we don't want to be detected, so we must take care to not disturb the automation process for now. So our backdoor must be tiny and fast. Otherwise, the underlying operating system, which is VxWorks, may stop the automation task because it will make too much time, for example. So the operator may be warned that something is going wrong with the PLC and maybe detect our attack. Also, we must take care about where to add our backdoor code in the automation code, because we need the ability to take control of the physical process if we want it. So hopefully Schneider helped us a lot to design our backdoor, because during the compilation task, for example, control experts can create logs which contain the assembly code of our automation program. So as you can see, they also provide comments with variable names and function names. So cool. This information were very helpful to locate where is the right place to inject our backdoor. And so the first payload we designed was just a memory dumper Thanks to it, we are able to dump all the mapped memory. So we've got the VxWorks code and also the Schneider Electric library code. And with all this data in our hand, we are able to do some reverse engineering and design a more powerful Modicon 340 backdoor. For example, the PLC can now make low-level connection, and also we can allocate large memory buffer and so on. So we can largely increase the Modicon 340 functionalities. So now I will try to explain how our backdoor works. So before the attack, the Modicon 340 runs a legitimate automation program periodically. So we get the legitimate automation program and we backdoor it by adding an ARM payload, which in fact is a download execute backdoor. Then we upload our program in the PLC using the existing connection with the engineering station. So from a network point of view, you just see that the engineering station is running a program in the PLC, so nothing strange. And after we make a stop and start sequence, so the Modicon 340 is running the legitimate automation program and also our download execute backdoor. And as we don't modify the legitimate automation code for now, the physical process is still running well. So now we build a malicious payload and we make it available on our command and control server. So our download execute backdoor will download it and execute it on the fly. I mean, without any start stop sequence. This kind of stuff is normally impossible to do with a Schneider solution. So, and it's important to mention that this malicious payload can alterate the physical process, for example, but not only, it can also make a network attack on another devices connected to the PLC local network. Or, for example, it can exfiltrate some internal document from a shared directory. And more generally, it can act as a proxy SOCs for an attacker in order to relay its traffic to the internal company network. And finally, when the execution of our malicious payload was finished, our download execute backdoor, remove it from the PLC memory, and wait for another payload to be downloaded from our command and control server. So we can now make online another malicious payload. Our download execute program will execute it on the fly, and so on. So now we will show you what we can do when we have our download execute backdoor inside the PLC. In this demo, we transform the PLC to a proxy. Personally, I think this feature is very interesting from an attacker point of view, because unlike standard computer like Windows or Linux, where it becomes harder and harder to maintain a backdoor access thanks to security appliance like antivirus, with this solution, an attacker got an access to the internal company network through the PLC, and it will be very difficult for forensic team to detect it and analyze such a backdoor, because there are no such tools available to do that easily. So in this demo, just as a proof of concept, we'll just show you a TCP scanner. So the attacker will build his TCP port scanner payload and make it available online in his command and control server. Then the PLC will download it and execute it on the fly, and then he will send back the port scan result to the command and control server. Okay, let me start the demo. Okay, so at the top left corner, we have the command and control console. At the left bottom corner, we have the simulation of the chemical process. And at the right bottom corner, we have the operate supervision screen. Okay, so the attacker will launch a TCP scan command, and many operations will happen in backdoor. In fact, the command and control server will compile a TCP scan payload. Then our download execute backdoor inside the PLC will allocate a buffer, download this payload, and execute it on the fly. So now the PLC will perform a scan on the IP and port that the attacker provided before. And then the PLC will return the results to the command and control server. So here we have just two TCP ports open, which are an HTTP port and a SSH port. And as you certainly noticed, there was no effect on the automation process. Okay. Oh, sorry. Okay, great. Okay, I will show you another demo. This time we make a Stuxnet type attack. I mean, we try to corrupt the physical process without any immediate noticeable effects. In fact, we build a payload that patches the legitimate automation program in order to corrupt the product composition formula. We also patch the composition level report to the supervision systems. So our download execute backdoor will get this payload from our command and control server and execute it on the fly like the previous attack. And as a result, the product composition will be corrupted, but for the operator, everything is going well because the composition value displayed by the supervision are fakes. Okay, oh, let's see it. Okay, so we've got the same layout than before. So now the attacker will type the command sabotage, which make a payload online on the command and control server. So as the previous attack, the PLC will download it and execute it on the fly. And at the bottom left, we have the real system. At the bottom right, we have the supervision screen. The final product is normally composed of 47% of product A, but our payload will slowly increase product A to more than 50%. And as you can see, the real composition is increasing, but for the supervision, the composition is still at 47%. Okay, and just to show you, if we stop to fake the values, then the supervision system gets the real values and raise an alarm. So normally we don't do this in a normal attack. Okay. So now we will show you the last demo of this talk. So in this demo, we break completely the industrial system. So we build a payload to make the input valve fully open, and we corrupt the pressure level to ensure that the supervision system do not raise an alarm during the attack. As the other demo, the PLC downloads our payload and execute it on the fly. So the pressure will quickly increase until the tank completely bursts. But for the supervision system, everything is going well. Let's see it. Oh. It was not a good slide, sorry. So as the other attack, we build our malicious payload and make it available on our command and control server. The PLC will download it. And you will see that the pressure increases quickly in the real system, but for the supervision, everything is going well. Okay. Okay, so now I'll let the floor to Nicolas for the conclusion of this talk.
Okay, for wrapping up after this nice burst, some key takeaways to have in mind. So if you have to deal with ICS environment, you have to know that it implies a large text surface because there are many Windows applications, there are many embedded systems, so the text surface is really tremendous. And so at least follow the manufacturer recommendation, disconnect the engineering station from the IT network, from the OT network. As soon you don't use it anymore, or you can also use a security appliance to monitor the traffic, do the best to avoid attacks. So even though ICS manufacturers start implementing security mechanisms, unfortunately, they fall into same mistakes in the early 90s years. And sometimes the vulnerability is not really easy to patch because it's some design vulnerabilities like the one Flavien has found about on the PLC. And sometimes it requires to do a lot of change in the software, and it's not quite easy. So the last thing you have in mind is that the PLC is really more than a basic electronic unit, because there is a full OS underneath with many related functionalities, many APIs, and as you can see through our demonstration, you can transform a PLC as a proxy forwarder, a network scanner, and many other things. So one recommendation I can give to people working with ICS is to invest more on deep dive analysis on red or purple team services to strengthen the overall security of such infrastructure. So thank you for listening us. If you have any question, you can ask now, but you can also contact us on LinkedIn or other way to contact. So thank you for your attention.